Okay, in this video, what I want to do is I want to um, solve for you a problem dealing with mixtures of gases and utilizing one of the applications that we saw once before, but we haven't really used yet in class, and that is the application where we have imperfect gases that we bring together and perform a thermodynamic process. And so in this particular problem, we are going to be looking at two rigid tanks that are connected together. In the first tank, we have 50% by volume hydrogen and 50% by volume carbon dioxide at a mixture pressure of 200 kPa and a mixture temperature of 20 degrees Celsius. And that is the larger tank. That is a 2 cubic meter tank. We then also have that connected to a smaller insulated rigid tank that contains oxygen at a temperature and a pressure. Then that will be our second tank. Now these aren't shown to scale, but we're going to assume that the first mixture is in part A, and the second mixture, which is only a single component, is in B. The valve then is opened, and it allows the combined system then to come together and reach thermal equilibrium. Now, during this process, there won't be any work, no boundary work, no paddle work, no electrical resistance work. There's also not going to be any heat transfer because both of the tanks are assumed to be well insulated. And so what we're after is then determining the final temperature, the final pressure, as well as the entropy generation. Now in this particular problem, they say go ahead and use the constant specific heats or the perfect gas analysis. And the temperature, pressure, and entropy values, answers are given here for a check. If you want to, you could actually go, and this is actually part of test, and you can see or watch somebody else actually complete this particular problem, but I'm going to be doing that myself. Okay, so we have a closed system type of scenario, and so we will be looking at that. So I want to bring up the test software, and again, as I said, this is actually is one of the hands-on examples in the NPG model mixing process. And so if you wanted to take a look at that, that particular application is under closed system, generic mixing processes. So it's this one right here. So clicking on that, and then when we ask for the substance is going to be a general gas mixture. And so we're going to be selecting this one here with constant specific heats. Okay, even though one of the tanks is a binary mixture, if all we were dealing with was the binary mixture, would be that. If they aren't identical mixtures, and so basically it's two or more different fluids as perfect gases. And so we are then going to be able to solve this particular problem. So what you see now in front of you is another test app that we really haven't observed so far. And so the first thing that's necessary in this particular app is, as you can see, we have a new tab. And that new tab allows us to select a number of different mixtures. And so in this particular problem, how we're going to work this problem is that we're going to say that in the left-hand side where we have the hydrogen and the carbon dioxide, that's going to be mixture A. And in the right-hand side where we just have oxygen, that's going to be mixture B. And then finally, for the final condition, that's going to be considered mixture C. And so once we get information about mixture A and mixture B, we're going to then make up a mixture C. Once we have those mixtures, then we can go to the state panel. And so in the state panel, you'll see that you can assign a state, but you also can assign which mixture. So we haven't set up any mixtures yet. So the state will have associated with it a mixture. And so let's come back here then, and let's put in the first mixture. And again, the information has been given to us in terms of volume. They say that it's 50% by volume hydrogen and 50% by volume carbon dioxide. And so as we get ready then to add the components, we can add them in however we want to. And so in this particular case, because we are told that it's by volume 50%, I now have selected that, and now I can go and I can find my hydrogen. And my hydrogen is, let's find a hydrogen. Okay, helium. Okay, here's the hydrogen atom. Be careful not to select that one. And okay, there's hydrogen right there. So I've just basically showed you a lot of what they have. So it is 50% by volume hydrogen. And when I put in the 50 here, I then can say add. And that comes over here for the mixture. And now I'm ready to then add the carbon dioxide, which is also 50%. And I can then add that. And so now what I have done is I've added these two components 50-50. And so over here in mixture A, you see that the mixture itself is 50 kilomoles of hydrogen and 50 kilomoles of CO2. If we actually had 50 kilomoles and 50 kilomoles, the mass would be as given here. We also see here is our mole fraction, and so our mole fraction between the two components is 0.5 and 0.5, and this is the mass fraction. Okay, because carbon dioxide weighs or has such a high molecular weight, we see that this mixture is 95% by mass and only 4% by mass of the hydrogen. So this process right here would allow you to solve the problem that we saw in the lecture notes with respect to the problem in the textbook, going between mole and mass fraction. We could have just as easily come over here and selected specifying our components on a mass basis, and then we could have determined what the mole fractions would have been. So we have gotten now our mixture A. Okay, so now the next thing we want to do is we want to specify mixture B. And so I'm going to come over here and I'm going to assign mixture B. And we know that mixture B now, everything is cleared out because I've selected a new mixture. And so now we know about mixture B, which is the right-hand side tank. It is simply oxygen only. And so we can put in, we can specify this any way that we want. Obviously, if we can put it in as just 100 kilograms of oxygen. We could put it in as 100% by mass of oxygen. We can put it any way we want. When we set up these mixtures, we really don't need to know the total amount. Okay, all we're doing is putting it in on a percentage or a certain mass amount. And then once we assign the state for that particular mixture, then it will calculate the volume and other things. Okay, and so for this one right here, we can just go ahead and say that it is, I put in a 1 here, 1 kilogram, and what it does then, it just generates for us the mixture itself. The mixture itself is oxygen, and again, because I just put in 1 kilogram, it figured out that it was a certain number of kilomoles, but again, this is only a relative number for our particular case. Here's the mass fraction, here's the mole fraction, and here's the molecular weight. And so now we have the mixture A and mixture B. And so I want to, before I talk about mixture C then, I'm going to go over to the state panel, and I'm going to put in the conditions associated with mixture A. So you'll notice that I have a mixture A and a mixture B here now. And so I'm going to say that the mixture A, which I've specified, is at 200 kPa at my pressure, and it's at a temperature that's equal to 20 Celsius. And so I now have put in my mixture conditions. Now, what else do I know? What else that I know is the tank itself. The overall tank itself is 2 cubic meters. And now, upon doing that, upon giving it the 2 independent thermodynamic properties and the total volume, it was then able to determine for that mixture of gases that the total mass was 3.77. Okay, so that's important to know, okay, is that we have 3.77698 kilograms for that mixture A. And so, and we'll see in just a second where that comes into play, okay? And so we have that defined. We also know that the molecular weight of this mixture is 23.01, and that's in kilograms per kilomole. And so this could tell us, if we wanted to, how many total moles there are. Now, in fact, it actually came through, and it now has each of the components. And so as you see, each of the components it has been determined. And what we see then for each of the components is we see some of the properties associated with the components itself. The enthalpy, the entropy, and so on. Okay, so we've gotten our mixture A in. Now we can go and select state 2, and state 2 is going to be mixture B. And mixture B is just the oxygen that's in that right-hand side. And what we know from the input, we know that the temperature of that side initially is 100 Celsius. And we also know the pressure is a fairly high value of 600 kPa. We also know the volume is 0.2. And so 0.2 cubic meters. And so for the mixture B, which is on the right-hand tank, we see that the total mass is 1.23776. And that's the amount of kilograms associated with the oxygen. Okay, and so with that in mind, we are now ready to determine mixture C. Okay, now before I do that, I'm going to go back to the composition panel, and I'm going to go back to mixture A, because there's something that I want to pick up. And what I want to pick up is what is the mass fraction of each of the two components. And so we know that we determined that the total amount of mass from state 1 was 3.7769. But what I'm interested in here is that the hydrogen was 0.04379 on a mass basis fraction, and we know that the CO2 was the remainder, 9562. And so since we know the total mass and we know the mass fraction of each of the components, then we now know the actual amount of mass that is in that tank that's on the left-hand side. For the oxygen, we already know how much mass is there. The mass is 1.23776 kilograms. And now we're ready. Now I'm ready to go in and actually designate mixture C. And what we want to do for mixture C is we want to put in the components based on the kilograms that we just determined. And so for the hydrogen, we see that the amount of hydrogen that's there is the mass itself, which is 3.77698 times the hydrogen mass fraction, which was 0.04379. And so that is then, when I add that, what I've done, what it actually has calculated is 165,393. And so that's the kilograms associated with the hydrogen that was in the left-hand tank. I'm now going to put in the CO2. Now the CO2 was equal to the same total mass, 3.77. 3.77698 times now the remaining mass fraction, which was 9562. And I have that entered, and I now add that. Now, upon adding that, we see that the amount of mass associated with the CO2 is 3611548. Okay, so what I've done then is I have taken the 95% of the CO2 total mass for the CO2 and the 4.3% of the mass being hydrogen, and I've put those in as the exact amount of mass for that. Now I want to add the mass of the oxygen, and so we know from mixture 2 or mixture B that the amount of mass for the oxygen was simply 1.23776. And so I can now add that. And so now what I have done is I've put in everything that was in mixture A and everything that was in mixture B, and I put it all in the right relative concentration. Okay. And so that's what I wanted to do. I wrote down some things. You could actually, because each of these components have symbols associated with them, you could have written it that way also. But I wrote the amounts down from the various mixtures, and so now we have our input, and you can actually see here that in the final mixture, which was mixture C, if I wanted to write that as a stoichiometric mole values that we will be discussing when we get into combustion, it turns out that this is what the equation would be in terms of moles. Again, we put the information in terms of the mass because that's what we had access to. And like I said, it calculated these mole fractions, and it used those mole fractions. Now you'll notice that the mole fractions here, 0.4, 0.19, 0.4, do not match up with these over here. Okay, but what they do is that they are they are in the right proportion. Okay, and so it's in combustion, all you had to have is the right proportion of the various mole fractions. You'll notice that it just so happened because of the 50-50 blend on a mole basis for the hydrogen and the CO2. That's why the 0.40 and 0.40, that's why the mole fraction is the same, and that's why these two numbers are the same. Okay, and then this is the relative moles associated with the other tank. And so a lot of information here. We've combined it all together, and now all that we have to do to finish out this problem is to tell the software what are the conditions associated with the mixture C. And so we're going to go to state 3, which is going to be mixture C. We're going to select mixture C. Now, what do we know about the mixture C? We know that it is the combined mass is mass 1 plus mass 2, because mass 1 corresponded to the CO2 and the H2 that was in the left-hand tank, and mass 2 was the oxygen that was in the right tank. And so we know that. We also know that when the valve was opened up, the total volume then now is shared by both of the two mixtures. And so we've now put in the mass and the volume. And as you can see, it did calculate the value of the specific volume, which is just the total volume divided by the total mass. However, and it did calculate the molecular weights, but it hasn't calculated the pressure and the temperature, because we still have to determine, or we still have to tell the software what the process was, and was there any heat transfer, and was there any work. And so now we're ready to go to the process panel. And now in the process panel, we see that we can now say the before state. The before state was state 1, and that was mixture A. The before state, the second before state, was state 2, and that was mixture B, and those were in the two tanks. And we have that little symbol. They are separated. There is a valve. And now what we want is the final state is where we bring them all together. And we bring it all together into state 3. And as you can see, state 3 then tells us that it's all mixture C. Now, what else do we know? We know that in this particular case, there was no heat transfer. Because the volumes, there was no volume change. It automatically figured out that there was no work due to shaft and electricity. It defaulted to that. And there was no boundary work. And since there was no boundary work, we see that there was no total work associated with the energy equation. And now what has happened is we see then that we do determine, the final temperature and pressure will be determined by the stored energy values and the masses of each of those. And that's equal to, in our case, 0. So basically conservation of energy. We have no heat transfer, and our boundary temperature really doesn't matter what our boundary temperature was, because again, there is no heat transfer. And so once I do a super calculate, it's then going to calculate the SGen based on the entropy associated with all of the states. And so if I hit super calculate, and now I go back and let me check out our states, it now tells us that state 3 is at this pressure and this temperature, and it did that through the conservation of energy. as well as the entropy balance information. And so now if I go back to the process panel, I see that the entropy generated is as given. So in this particular problem, the answer of the entropy generation was 0.923, as we see here. We go back to the state panel 3, and the temperature in Celsius was 33.1 as given in the problem, and then finally the pressure, the final pressure, was approximately 235. Okay, and so that then corresponds to the problem that we had assigned here. So we see that this was a problem wherein we were able to bring two mixtures together and form a third mixture. We had to do a little bit of math or accounting to make sure that we put in the third mixture in the appropriate proportions. And then we were able to perform the process with the right amount of work, the right amount of heat transfer, and the software then solved the conservation of energy. The conservation of mass is already defined, or is already solved because we made it solved, and then the conservation or the accounting of entropy was also used to determine the entropy generation associated with the irreversibility of this mixing process. And that then finishes up this one and allows us to see then that we could use that particular application to define our mixtures and also to perform our processes. And so the uniqueness of this particular problem was the first time that we've seen this composition panel, and as also once we obtained the various compositions, the various mixtures, we were then able to assign the mixtures to the various states, and then that allowed us then to actually set up the problem to bring two mixtures together to form a third mixture and to get the information that was necessary.